one of the long-running kind of goals of sort of the mathematical style of science is make predictions about what's going to happen in a system. One is if one is feeling good about one's work in celestial mechanics or something, it means one can predict where this planet is going to be at sort of any time in the future just by solving the equation, so to speak.
Welcome to Close to the Truth. I'm speaking with Stephen Wolfram, the distinguished physicist, computer scientist, and software entrepreneur. We discuss in depth the Wolfram Physics Project, Stephen's grand, indeed radical, vision of a new kind of science in which computation via simple rules is the foundation of physical reality. The Wolfram Physics Project is a Close to the Truth multi-part series. This is part two on foundations, computation, and cellular automata. Stephen, let's start by just a quick review of what the Wolfram Physics Project is, and then let's understand its foundations.
So the question is, what's the universe made of? And the concept of our physics project is ultimately it's all made of computation. So let's talk about perhaps kind of how that could possibly be, what computation can make.
Yes.
And this is sort of something that I started doing in the 1980s, was sort of thinking about how could one base science on thinking about things in terms of programs. It kind of the history had been sort of in the 1600s, this sort of transformation of science based on the idea that you can describe the natural world by writing down mathematical equations. That had worked well for some purposes, had not worked well for systems whose behavior was more complex. And so I was interested in what kind of foundations could you make for those other kinds of systems. What I thought about was, let's just use very simple rules where we define the rule, then we think of that rule as corresponding to a computation, and we run the computation, we see what happens. So I got, it's a question of sort of what do simple rules typically do? And it's kind of felt like one had this kind of computational telescope that one could turn out into the computational universe and see what was out there. So a very simple class of rules I started studying were ones called cellular automata, where you just start off with a row of black and white cells, and then in a series of steps, you update the color of every cell according to some fixed rule in terms of the colors of its neighboring cells. So for example, you might get a pattern like this produced, where we start off to just one black cell, and then in a series of steps, we're just filling in cells according to a particular rule. If we kind of look at what we get from doing this, at the bottom is sort of a representation of the rule of how we go from a cell and its neighbors to the configuration of the cell on the next step. In this particular case, we have this very simple rule. We start off from just this one black cell. We get a very simple pattern of behavior. Now, I had at first assumed that if the rule was that simple, the behavior would somehow be correspondingly simple. But I started trying other examples. Here's another one where the rule is same type of rule, but now you get a checkerboard pattern. Or here's another one where you get a kind of more intricate kind of pattern. If you continue that a while longer, it makes this nested kind of fractal pattern. But then, kind of a critical thing that I did back in 1981, I guess it was make this kind of picture. I just looked at all possible rules. I'm just looking out into the computational universe of possible rules. I'm looking at all possibilities of a certain kind. What do they do? So many of them do very simple things, but Rule 30 is my kind of all-time favorite science discovery. Here's what it does. You just started off from one black cell at the beginning. You have this very simple rule for how the pattern is made. And yet, if you run that pattern for a while, you get this kind of thing. You get something which looks very complicated. There's a certain amount of regularity that you can see over on the left, but many aspects of this pattern look complicated enough that for all practical purposes, they seem completely random. And this, for me, was a sort of a key moment, because it kind of broke my intuition that in order to get complicated things to happen in nature or elsewhere, you necessarily had to have complicated rules underneath. This was showing that you could have simple rules underneath and yet get complicated behavior. And I kind of very quickly started thinking that that was sort of the secret that nature is using across physics, biology, other areas to kind of make the kind of complexity that we see so often in the natural world.
Mm. And so, how many different kinds of rules, like Rule 30, have you explored? Just order of magnitude so we can get a sense.
Well, gosh, I spent a decade doing very little but exploring these kinds of things, and I continue exploring more and more different kinds of rules. So it must be, oh gosh, it's hard to estimate that. I mean, it's a question of whether you say ones that I have personally looked at or ones that computers have looked at for me. Ones that I personally looked at, I bet I'm pushing, oh, probably close to a million by now. Ones that computers have looked at for me, certainly trillions to quadrillions. And I think, at some level, the thing that is really remarkable to me is this idea that simple rules can produce complicated behavior is it keeps on being the case even today that I say I'm looking at something, I'll say, well, I can't imagine that a rule that simple can do this particular thing that I'm looking to see happen. And then I'll try running it and I'll realize, well, it managed to do it, but in a way that I had never imagined. It kind of
We're talking about simple rules, I understand, like Rule 30, the simplicity of those kinds of rules, which is indeed remarkable. But as you get into a million that you've looked at and trillions that the computers looked at, are these just, are they still simple, or are they compounding different kinds of simple rules and putting them together? Because that could be infinite.
No, no, they're pretty simple. It doesn't take long before, if you're getting a picture like this might be, rule 30 is the 30th rule in a sequence. This one might be the millionth rule in some sequence. Or you don't have to go far in the computational universe before you start seeing all kinds of elaborate things happening. I mean, this is the really surprising thing in the computational universe, that you don't have to set things up very carefully to figure out which of the one in a quadrillion, quadrillion, quadrillion rules you're looking at. You just go and sort of sample the computational universe, and very quickly you're seeing behavior that's immensely complex.
Hmm. How does the principle of computational equivalence interrelate with all of this?
So one of the questions is, we made an empirical observation. Out in the computational universe, complex behavior is very common. What kind of general principles can we use to think about what's going on? And for me, the most important is what I call the principle of computational equivalence. And here's how that works. We think about any of these kinds of processes of making one of these patterns as a computation. We start from some initial conditions, some sort of input, we apply some rule, and as we produce this pattern, we're effectively doing a computation to make that pattern. So the question then is, how do the different kinds of computations that make different patterns, how do they compare? Sometimes the patterns we're making are really simple. We can say, well, that's a kind of trivial computation that's being done there. What I observed starting in the 1990s was that above some very low threshold, it seems like all the computations that are getting done are equivalent in their sophistication. It's not the case that once you get to rule 30, you've got to sort of one level of complexity. Then when you get to rule a million, you get to another level, and rule a trillion, you get to another level. Above some very low threshold, as soon as the behavior is not sort of obviously simple, you immediately are in this zone where you have everything has sort of an equivalent sophistication of the computations it's doing.
Yeah, the word equivalent is very strong. I mean, that is not intuitively obvious.
No, it is not. I mean, there's a precursor to this from the 1930s, which is the idea of universal computation.
Okay, yeah.
Before the 1930s, people might have said, oh, you want an adding machine, you want a machine that plays chess, you want a machine that does this. Each of those will be a different piece of hardware, a different machine. But then what became clear starting in the 1930s, although the full import of this wasn't clear for a really long time, that you could have sort of one underlying universal machine that could be programmed to do all these different kinds of things. Now people, I should say, by the 1980s, when I was starting to work on this, people didn't believe that that sort of universal computation idea applied to things like physics.
Yeah.
They always thought that that was sort of a separate branch, and that sort of computers were a thing that engineers made, so to speak, not a thing that showed up in the natural world. And the big surprise when I started exploring the computational universe of simple programs was that even these very simple programs could show this very complicated behavior. It wasn't that you needed to do the engineering to build up a thing that you could call a computer, so to speak.
Hmm. Okay. Given the principle of computational equivalence, and running all these different programs, you would think that the total space that is created based on the different kinds of rules would have no uniformity or homogeneity. But you say that's not the case. There is a certain coherence to the space that these all these different simple programs in under the principle of computational equivalence, that there is some kind of a structure to this space of everything that they create.
Yes, I mean, this is the organizing intellectual principle is what you've got are lots of computations that are somehow equivalent in their sophistication. And that has many consequences. So here's one that I think is perhaps the most important consequence is the phenomenon of what I call computational irreducibility.
Hmm.
So kind of one of the long running kind of goals of sort of the mathematical style of science is make predictions about what's going to happen in a system. One is if one is feeling good about one's work in celestial mechanics or something, it means one can predict where this planet is going to be at sort of any time in the future just by solving the equation, so to speak. And just by getting the solution, plugging in the number for what time you want, and seeing where the planet ends up. So there's this kind of idea that by being smarter with all your equations and so on, can do a much simpler computation to work out what will happen than the system itself has to do. It might take the Earth a million years to go around a million orbits, but you can just immediately say this is where the Earth will be a million years from now. So what the principle of computational equivalence implies is the phenomenon of computational irreducibility, which is essentially saying that when you look at one of these patterns and you ask what will happen after a billion steps, for example, the only way you can reliably tell the answer to that in general is just run those billion steps and see what happens. So, in other words, this idea that you can kind of jump ahead, you can computationally reduce what's going on, and sort of by being smarter, know what's going to happen.
You can't.
Computational irreducibility implies that won't be the case.
Hmm.
And computational irreducibility is sort of a consequence of the principle of computational equivalence. Here's how. You say, we've got one computation going on that's this system, maybe a simple rule that's just generating this pattern. We've got another computation going on that's us with our brains, our computers, our
Hmm.
mathematics, whatever, trying to outrun that
Hmm.
computation. Well, if it wasn't for the principle of computational equivalence, we might think we can outrun that computation. But the principle of computational equivalence says we're stuck doing a computation that is equivalent to the computation that this very simple rule is doing. And that's why we have computational irreducibility.
Hmm. How important is the underlying mathematical languages that you've developed in the foundations that leads to the Wolfram Physics project?
Well, okay, so I've spent my life kind of building tools for myself to use and for other people to use. And kind of the arc of that story has to do with kind of making a computational formalization of the aspects of the world that we care about. So, kind of if we look at the history of, I suppose, for our species, probably the single biggest invention was language. And language is sort of a first formalization of the world. We don't have to like point at individual rocks. We can just use the term rock to refer to all these different rocks. Then we have things like logic. Then we have mathematics. These are kinds of ways to formalize our thinking about the world. Now we have computation as a way to formalize our thinking about the world. And what I've built is an effort to kind of make sort of a computational notation for talking about the world. So, for example, if you go back 500 years, when people were talking about mathematics, they were just using ordinary language to talk about mathematical concepts. And then mathematical notation got invented, plus signs and equal signs and things like that. And that's what allowed algebra to get started, calculus, led to the mathematical sciences. My kind of goal with what we now call Wolfram language is to have essentially a notation for computation, a way of talking about the world computationally that can lead one for sort of all fields X to computational X. Now, it's a little bit of a tricky story because that the foundations of that computational language are sort of deep computational ideas which turn out to be more related than I ever expected to our physics project. It's kind of a bizarre irony that the things that I invented for sort of practically building this computational language turn out, and maybe we'll talk about that later, turn
What's
out.
just one example of that? Give one example of an element of the computational language.
Right. So the big idea is to represent everything symbolically. So
Yeah.
what does that mean? We have a number like two. We have a thing like X. In algebra, you have X can stand for anything. In our symbolic language, there can be a symbolic thing that represents a city or an image or a sound or a person. And then we can compute with that. So, for example, we can say, you know, give us a list of, I don't know, all the capital cities in Europe. Then we can take those as things that we can compute with, work out, what's the shortest tour going through all of those cities or something like that. So that's kind of a foundational idea. Another foundational idea of computational language is that you can think of everything in terms of transformations between symbolic expressions. That if you say, I'm going to do an operation, like I'm going to add these two numbers together or these two algebraic expressions together, you can think of that as taking one symbolic expression and transforming it according to a certain rule to another symbolic expression. And you can do the same kind of thing when you're thinking about doing some operation on images or something like this. That foundational idea that everything can be represented as a symbolic expression and the actions that you do are transformations between symbolic expressions, that's sort of the foundational idea that leads to our computational language. And that idea is sort of worked out in a very practical way in computational language, also happens to be very closely related to what turns out to be what one is doing when one is thinking about sort of these computational foundations for physics. But I didn't see that. It took me decades to see that connection, which is kind of ironic because it was a thing that I had been building for a long time. But in terms of what I see these simple programs out in the computational universe, that is computation in the wild. That's computation unfettered by any sort of connection, so to speak. What I've been building with our computational language is both a foundation for computation and a way to do computations of the kind that we humans have thought are useful so far.
Right.
And so, in fact, in a sense, the when we'll talk about the Rulliad is sort of a story of all possible computation, and most of the Rulliad is things that we humans have not yet cared about. Gradually, as we advance in the paradigms we use to think about things, we're getting just a little bit further out. But what I've tried to do in our computational language is to capture sort of humanized computation, the kind of computation that we think we care about so far. I mean, it's worth remembering that sort of if we think about science as an activity, the way I view science is it's kind of this bridge between the natural world as it is and what we can understand with our finite minds, so to speak. Science is this effort to sort of make a narrative that is understandable to us from what is actually out there in the natural world. And it's the same kind of thing here. We've got what is out there in the computational universe, and we've got the kinds of things that we humans think about. Computational language is kind of the general bridge between those things.
Good. I just want to go back to the principle of computational equivalence because one idea that I think you have, if I got it right, it just seems counterintuitive, and that's that there's only one ultimate equivalence class for all computations. Is that right?
That's right. That's right. I mean, well, let's put it
What?
this way. Things, many things get to that level. There are things below that level.
Oh,
If you have
okay.
something that is just going 1 0 1 0 1 0, just repeating itself periodically
That's trivial, yeah.
forever, then it's quite trivial. But as soon as you get to above the trivial, so to speak, there is this one uniform level of computational capability. And as I say, the first surprise of that kind is the idea of universal computation. That's the idea
Uh,
that led us to software, led to the whole computer revolution. That idea has already
yeah.
been the idea that something like that, that it is possible to get to universal computation is an idea that's already, had a big effect in the world. The fact that sort of computational equivalence is ubiquitous, and computational equivalence goes a bit further than just talking about it is possible to program it to do this. It says the computation that you will generically get, even if you start from one black cell, is already an arbitrarily sophisticated computation.
Mhm.
So in a sense, it's a continuation of the story from about 100 years ago of Gödel's theorem and Turing machines and other kinds of concepts that led us to this idea that universal computation was possible. This is saying universal computation is ubiquitous, and it's more than just what can be programmed. It is what generically happens, and it applies to the natural world as well as to the kind of formal world of things that we can construct.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing. Closer to Truth is now accepting your tax-exempt donations. Please come to closertotruth.com/donate. Thank you very much for supporting us, and thanks for watching.